All right, welcome to the second session of the day. This is the elephant in the room session. It's the robot learning session. We'll have 5 contributed talks, and we'll kick it off with Sanjay Krishnan from Berkeley. Please join me in welcoming Sanjay.
Let's see. Oops, there, good, perfect. Just wanted to make sure things go. Okay, thank you all for having me. Today I'm going to talk about an exciting new extension of inverse reinforcement learning to sequential problems. I'm Sanjay Krishnan from UC Berkeley. I'm from Ken Goldberg's Auto Lab. So before we get started, let's talk about inverse reinforcement learning. Inverse reinforcement learning is the following problem. Suppose we have a dynamical system, and we observe trajectories of a controller on this dynamical system. The goal of inverse reinforcement learning is, as the name actually sounds, is to infer what the control objective of that controller was. So for example, if we have a quadratic cost matrix, it is to infer the Q and R matrices. And this was popularized by Stuart Russell in the 90s, and many of the initial ideas actually date back to Kalman in the 1960s. So inverse reinforcement learning is not just because of intellectual curiosity. It has a number of important applications in robot learning from demonstrations. For example, suppose we wanted to teach an autonomous car how to parallel park. One thing we might do is to have a human sit in this car and in different configurations show us how to parallel park. What we would do is we would take these demonstrations, we'd infer some sort of a reward function. We'd say that maybe this demonstrator is kind of minimizing the distance between the two cars, kind of getting right to the center point. And then given a new instance of this task, for example, with different cars or perhaps a different driver or different kinds of dynamics there, we want to turn that reward function into a new policy. We solve the forward problem, we do a policy search problem. And if we actually look through recent literature, it's actually increasingly popular for this policy search to be a reinforcement learning algorithm, because we want to be robust to the new instance having new dynamics or some unmodeled phenomena that we didn't see in the demonstrations. Now, the interesting part about this 3-step algorithm is that the rewards that you learn are actually really important. For example, if we learned a really sparse or delayed reward function, like a delta function, it would take a lot of exploration to solve this new task instance. And we come from a background of robot manipulation, and we were particularly interested in multi-step tasks such as robotic surgery. We can collect a whole bunch of data on surgical robots of, say, surgeons cutting something in gauze. Now, modeling something like this turned out to be really hard in an end-to-end way. If we actually threw an inverse reinforcement learning algorithm at this, we would get something that was technically right. We would get some sort of goal state or a perceptual final state, but the problem is it would summarize this really complex sequence of actions and not actually show the agent how to get there. And these issues, we see this in classical control problems and in these increasingly popular Atari games where these long-term delayed rewards. So we decided to explore a variant of this problem. Instead of trying to infer a single reward or a cost function, can we have a task model where we look at a sequence of reward functions? So that is that there is a sequence JSeq 1 through k, and the agent accumulates cost or reward with respect to each one of these functions until a transition condition is met. And the transition condition is just a subset of the state space. And because this is kind of an initial step in this direction, we made a bunch of simplifying assumptions, and we explored the case where the system is a linear quadratic Gaussian system. That means that locally, the agent is applying linear control, and the transition regions are also Gaussian probability distributions, and our cost functions are quadratic. And we also make some regularity assumptions that I encourage you to read the paper about non-degeneracy about the particular rewards. So based on these assumptions, I'll kind of give you guys a high-level overview of what we did. It's basically an IRL algorithm for reward and transition inference in these sequential tasks. We have a 3-step process which kind of breaks down intuitively. We first do a segmentation thing where we break this down into the different reward sequence, into the different parts of the trajectories that correspond to the different rewards. Then we solve IRL problems locally, and then we finally do a policy search problem, and that's actually our metric for evaluation, like how efficient is that policy search, because we've kind of reduced the time horizons and included new structure into the problem. And this is definitely inspired by a lot of related work by Peter, by a whole bunch of other people in the community, and also draws from a lot of ideas from Bayesian inference as well. And there are actually a number of applications in this conference that we've heard of. I think the last talk about these kind of plannings in those reconfigurable robots, actually naturally this relates to hierarchies and control hierarchies and things like that. So let's start with the first step of this algorithm, segmentation. Suppose we forget about the reward functions and we just want to infer these transition regions. The first thing that we can note is that if we look at the assumptions that we made, the closed loop dynamics of this system are locally linear. That means that when the rewards transition, the local linear closed loop dynamics also transition. So it kind of models a switch linear dynamical system, and this is a system in which we actually understand parameter inference pretty well because it's kind of in a fully observed process. So we can actually do a first pass where we figure out these transition points in all these trajectories with expectation maximization, figure out which points are likely transitions. Then what we can do to actually turn these into transition regions, we can cluster over these transition points. So that means we can fit a Gaussian mixture model to this. And one of the challenges with all these kinds of mixture models is how to set the number of components, and we can leverage new results from Bayesian statistics to use something called a Dirichlet process to put a soft prior that flexibly grows with the data on the number of transitions. And this was a subject of our prior work at ISRR 2015. But the basic idea is we can actually get these transition regions. And what this ends up looking like is if we look at the circle cutting task before, we're going to get this mess hairball of trajectories, and we can turn these into Gaussian confidence intervals of where transitions occur. So where did switching events happen? And we can concisely summarize it as that. And this is kind of the first step of the problem. So now that's only half the battle, right? We've gotten these transition regions, so we can look at a set of trajectories, a set of demonstrations, and figure out where did transitions occur, and we can kind of summarize them over the state space. So now, how do we actually turn those into local reward functions? Now, the interesting thing that we realized was that this two-step process actually had a really important property. The transitions that we were learning, the segmentation algorithm that we had, was only dependent on the current state. It is sort of this testing contestable property that did the agent enter this confidence interval. And this is not true of all segmentation algorithms. In some sense, segmenting the task did not depend on knowing where the agent would be in the future, right? So this preserves the kind of MDP structure of the problem locally. So what we can do is now we can actually fit a local quadratic reward to the thing. So I'll kind of walk through what that math looks like. So let's kind of simplify this out as thinking about j of x, and this is just a quadratic cost. We can kind of put the state and action into the same big vector, which is boldface x. We can write this actually as a linear function of the matrix parameters by doing a dyadic expansion. Then we can figure out how do we kind of frame this as a probabilistic problem. Let's come up with a probabilistic model for how we believe that that cost term actually affects demonstrations. So we can actually say that segments that had a higher reward or a lower cost basically were exponentially more likely. So we can actually put this as a Boltzmann distribution. So we can put a probability over the observed segments and try to figure out the most likely Q that generated a particular set of segments. So what best explains it? Turns out with Boltzmann distributions, the distributions we all love, because when you take a log of them, they just turn into linear functions up to some normalization, and we can solve it really efficiently in a maximum likelihood type of setting. And this is a variant of maximum entropy inverse reinforcement learning, if you guys are familiar from out of CMU. So what does this do? So let's kind of take a step back and think about our circle cutting problem. What this basically does is we've first segmented the task, and then we've assigned these quadratic costs to each one of the segments. What that's basically going to do is it's going to tell us at each one of these segments what was the agent controlling for. So what was the human actually controlling for? Were they controlling distance to the line? Were they controlling torque? Maybe were they controlling something else? And this kind of gets you this cost matrix that we want. Now finally, we can't just throw up our hands in the air and say we got a reward function, we're done. We actually have to turn this into, given a new circle, how do we cut this, right? And this policy search problem actually turned out to have one subtlety. Because the first thing that you might want to do is you've segmented this problem, and you could do reinforcement learning locally on each one of these segments. The problem is, if you're trying to do some sort of a Q function regression or some sort of function approximation, you're throwing away a lot of the structure of the task that is shared across each one of these subtasks. So you'd ideally like to solve the entire problem at once. But the challenge is that these segments have this sequential ordering, which kind of violates the MDP structure. So you need to have additional bookkeeping to basically track the progress of the task as it goes on. Which segments have you previously achieved, so there's no ambiguity in what you need to do. So this is an example of how we can modify a reinforcement learning algorithm to account for this. This is basically your Q-learning. This is basically your Q-learning formulation. We would add additional features that basically test and track like a counter that basically counts. These are the previous segments that I've crossed into. And because of these nice Gaussian confidence interval structure, we can actually pretty efficiently test this. So let's actually look at a first simulated example of what this does. So we have this acrobat, which we heard earlier in this conference. It's basically a two-link pendulum. It's a chaotic system. We have a reward function that it needs to cross above that kind of orange horizon up there. So now what happens when we directly apply RL to this problem to learn a controller that does that? It actually works pretty well, but it takes a lot of time to converge. Now suppose we were to take that RL algorithm and do some sort of an inverse reinforcement learning. Now learn a slightly better shaped quadratic function to go up there. You get a slight improvement, but not too much more. Then what happens is if we actually break this up into a whole bunch of subtasks with shorter horizons with these quadratic rewards, we get SWRL, which does a lot better than that. And this is sort of intuitively what, from a control theorist perspective, instead of just putting an end-to-end RL on this, would kind of do, right? You would locally linearize and you would solve local objective functions. So this is kind of intuitively encoding that. And you might wonder what happens if we just try to function approximate the whole thing from the RL, try to memorize the sequence of the trajectory sequence. That's kind of supervised learning. It doesn't do too well because of the presence of noise. So now we actually did this on a real physical setup where we tried to do this cutting task, cutting arbitrary curves, where we trained on straight line curves. There was like a two-step thing where you first set a position and then you have to cut along the curve. And we have some initial promising results on this, that the technique can actually be applied in a real robot, which is kind of cool. But this is kind of emphasizing the differences that the demonstration dynamics are often substantively different from execution dynamics. And as with any learning talk, as we've learned in this conference, there should be multiple dirty laundry slides. But the interesting thing is we constructed a whole bunch of domains that satisfied the assumptions, but we actually didn't do too well. And there's really a problem with over-segmentation in these settings. When you over-segment, the local function approximation, the local quadratic functions become harder to fit. So when you do when you have maze-like environments where everyone goes through the same path, but you add a segment that shouldn't be there, it's not actually that informative. And we can actually do worse than baselines. And there's a lot of work to be done, and we're trying to actively fix this right now. I'm going to wrap up by saying that in future work, we're actually really interested in segmentation as a way of facilitating a bridge between learning-based and analytic-based methods. Because what this allows us to do is to break up a task into a lot of concrete local objectives, and reward functions is kind of a language that both sides speak. We speak this language of reward functions in planning, we speak this language of reward functions in reinforcement learning. And the idea is we can kind of pick and choose the best technique for the particular primitive that we're trying to learn. And we have some initial results where we have to do this kind of two-step process where we're using our learning-based controller to cut, and we're using a robust feedback controller to basically tension and stabilize the gauze when certain pins have basically been dropped. So that's basically it. There are a lot more experiments in the paper. I was able to show only a few things, but feel free to talk to me afterwards. Thank you.
For questions, let's start with our respondent, Tomas Lozano Perez, in the back there.
So I was wondering, you showed comparisons to a couple of methods that didn't do any segmentation.
Yeah.
And it shows that the segmentation is very valuable, which
Yeah.
I quite believe. But then I was wondering about Q-learning on a real robot.
Yeah.
I mean, is that really feasible? For example, comparing to something like what Scott Meekham did, in which he did segmentation and then he learned a DMP, a dynamic motion primitive, which would typically take fewer samples, I would expect, than trying to do Q-learning from scratch. Do you have any comments?
Yeah, absolutely. I completely agree. Q-learning was just so we could keep our simulated experiments and our robotic experiments consistent. It took 30 minutes of trials to basically get anything working, and there was a highly curated state space where we basically, one of the features was the distance to the line, and we had discretized the action space. So I completely agree that there are practical aspects in applying straightforward reinforcement learning algorithms, but I believe that the same ideas will still hold to the new trajectory-centric forms of RL that we're looking at, like guided policy search. It would even apply to these these kinds of things like dynamic motion primitives, but that's I think that's an important question that we're exploring in the future. I think that's absolutely right. And in our prior papers, especially we've compared segmentation performance to the BPAR HMM method that Scott Neekum used, and also some of the skill tree methods that Konidaris used. That was kind of a segmentation result. This was kind of connecting it to it. But I completely agree that there are practical challenges in applying reinforcement learning on physical systems.
Thanks. Really interesting stuff here. I was wondering a bit about the first video you showed where it's cutting the circle of gauze and the surgeon's kind of dropping it several times and there's errors. And how to basically not include those in the computation of the cost function, or maybe to include possible error modes that can happen.
Great question. So this is something that I kind of glossed over. One thing that you can actually do when you construct these Gaussian mixture models is reject models that do not contain sufficient data from all the different demonstrations. So suppose you collect 10 demonstrations and there are a whole bunch of spurious outliers. You can look at the mixtures that are either very sparse, that don't have a sufficient coverage, or also not representative, that it was only one person's. So that allows you to keep things consistent. But doing those kinds of prunings actually requires you to have pretty strict assumptions about what those demonstrations look like. Like they all follow the same partial order and things like that. But yeah, that's a great point.
So I have a question.
Yeah.
What are your thoughts on using raw visual inputs, and what would it take to get that to work?
Great question. We're currently working on a project where we have we're trying to relax the linearity assumption, and we're trying to arbitrarily parameterize the local primitives. And it looks like the best idea that we have is a two-step process where you first do unsupervised learning, where you basically do some sort of an autoencoder, or you do some sort of a contrastive diversion, the contrastive thing on like these restrictor Boltzmann machines, kind of marginalize the vision problem out of it, then do simple like local linear control like based on those features. But we don't. It's active experimentation right now. We don't actually have a good answer to it.
Colleen, could you come sit up during the last question? Yeah, over there.
Hi, quick question. See if I understand right. You assumed that you knew your linear dynamical system model quite well. How sensitive is the technique if your model isn't that well known?
Good question. So what we do is we actually infer the linear dynamics as a part of the segmentation. It is definitely sensitive to that. I think that the biggest thing is that if they're sensing noise, a lot of these algorithms are actually not robust to partial observation. So we know that sysid is a relatively straightforward problem. Like even with just one mode, is a relatively straightforward problem when you have perfect observation, just linear regression. But when you have noise and you have an observation matrix, suddenly it becomes a really complicated problem. So definitely this is an issue, and I think definitely, especially with the real surgical results, like the reason that we have very big confidence intervals around those clusters is partly due to this reason. So it is sensitive to it.
So I know there were a few more questions, but let's defer those to lunch break, and let's thank Sanjay again.